Now we collect the term involving h. So this is FAGA. What's FAGA? FAGA is the value of the inner product, FA inner product of GA. Sorry, I forgot a dot here. So FA dot GA is the value of the inner product function f dot g at the point A, which is plus f transport A g point A plus g transport A f point A, then h, then theta h. So we will prove as h goes to 0, theta h divided by the norm of h is 0. So from this equality, and this limit is 0, we see that the derivative, the inner product is differentiable at A, and the derivative is here. Derivative at A is here. This is the metric A, corresponding to the metric A in the differentiability, in the definition of differentiability. Okay, so this tells us that the derivative of f dot g at the point A is this two terms, the sum of these two terms. This is precisely our conclusion here. Okay, so to conclude the proof, we will prove this result. The theta h is the expansion, removing the three terms we already studied here. So you can check. We will do this in the next page. You can check that theta h. What's theta h? Theta h is the inner product of FA with delta h plus the inner product of eta h and GA. And plus f point A h g point A h plus f point A h delta h plus eta h g point A h and plus eta h and delta h. You compare the expansion and the terms we already studied before. You see that our remainder term theta h consisting of these 6 terms. These terms, we have a look on these terms. There are 3 types, maybe 4, several types of terms. These 2 types are the same type. And these 2 terms are also of the same type. Finally, the last 2, this is a type, and this is another type. So we for each type, we only study one of them is enough. So we will consider this term. Consider this term, the first term. The first term, we need to prove that theta h divided by the norm of h goes to 0. So we need to prove that every term has this property. If every term has this property, then the result is proved. Okay, so FA delta h divided the norm of h. What's this? Here, FA and delta h are element in Rm. This is the inner product, the absolute value of the inner product. By the Cauchy Schwarz inequality, this will not greater than the norm of FA multiplied the norm of delta h, then divided by the norm of h. This goes to 0. Why? Because our delta satisfies this property. Okay, so this goes to 0. Therefore, the first term is okay, and this term is okay. No, maybe I read. This is okay. This is also okay. Similar, and the third term. For the third term, we consider the f prime a h inner product with g prime a h. Then this apply the Cauchy-Schwarz inequality again. This will not greater than the norm of f prime a h multiply the norm of g prime a h, then divided the norm of h. Then for these two here, for these two f prime ah and g prime ah, we apply the metric norm. We apply this again and again. Ax will not greater than the norm of a and the norm of x. Okay, so apply this result. This will not greater than the metric norm of f prime a and the norm of h, the metric norm of g prime a, the norm of h, then divided the norm of h. So a norm of h is cancel. These two terms cancel. But we still have a norm of h here. So this goes to 0. As h goes to 0. Okay. So this is also done. And so this is also done. And now we consider the first term in the second line. Here, f prime a h delta h divided by h. Again, applying the Cauchy-Schwarz, this will be f prime a h delta h under the norm of h. Then for the first term here, we use the metric norm again, the norm of the metric f prime a, and then the norm of h, then delta h, then divided by the norm of h. Now the norm of h cancel, and you will get this goes to 0 because delta h goes to 0. As h goes to 0. Why delta h goes to 0? Because if not only delta h goes to 0, even after divided by the norm of h, it goes to 0. Therefore, the denominator must go to 0. Okay, so this term also done. And this term is similar. The last term here, the last term can also be studied very easy. Let's see. The last term is delta h eta h. So delta h eta h. This will not greater than the norm of delta h, the norm of eta h divided by h. But now, for example, eta h divided by h already goes to 0, and the delta h also goes to 0. So this is the two term, the product, the multiplication of two term, both term goes to 0. Therefore, the result is goes to 0 as h goes to 0. So this proves this important result. Computing the derivative of the inner product of two vector valued functions. Because for real valued functions we have more ideas. While for vector value functions, it is more difficult. So sometimes we need to transform the problem on vector valued function to problems of real valued functions. So in this case, when we want to compute the derivative, this result is very useful, because a very useful idea to transform a vector into real numbers or scalars is by taking inner product. Okay. Now we want to study another important problem. We have learned differentiability and the derivative, and we study the consequence of differentiability, that is continuity, and also we study the computation of derivatives. Okay, linear combination, inner product, and the other way is the other important problem is by composition. We know the nonlinear maps we are encountered is complicated, but usually it can be decomposed into several simpler maps. Okay, so the way of decomposition is linear combination and also composition. Okay, so if two maps are differentiable, so how about their composition? We expect that the composition is also differentiable at corresponding points. But even it is differentiable, how to compute the derivative of the composition? Okay, all these are problems we are now want to study. So the situation is like this. G is a map from an n-dimensional ball that is a neighborhood of A to Rm. And the F is a map from U to another Euclidean space L. So if in the case that image of G is contained in the domain of definition of F, that is U. In this case, we have a composition. Composition is F is equal to G. The composition is a map from R neighborhood of A to RL. The composition is given by the value of the composition at the point X is F Gx. This is meaningful because Gx, by this condition, Gx is a point in the domain of definition of F. Therefore, we can apply F to Gx to obtain a value in RL. This value is defined to be the image of the point X. So this defines a map from BRA to RL. This map is called a composition of F and G. Okay. So we can express this situation by this commutative diagram. So this is BRA G into U. U is a subset of Rm, and F is defined on U in RL. So this is the composition. Okay, so a basic problem is that if G is differentiable, the question we will study. If G is differentiable at A and F is differentiable at the corresponding point B. B is the image of A, under the map G. So the question is, the composition differentiable at A? If yes, the derivative at A. Okay, this is the question the chain law will address. Okay.